Hey there, AP Pre-Calc people. This is Miss Adams from Flamingo Math. In this next lesson, we're going to have 3 days of solving trig equations and inequalities. Let's take a look at what's involved in this lesson. We see here that equations which contain trig functions can be used to answer periodic behavior in our world. So we'll see some practical applications. We can predict the tides, moon phases, seasons, breathing intervals, and so much more modeled with a trig equation or a trig function. We will also see how we can use inverse trig functions to solve equations and inequalities that involve those trig functions. Let's jump in here with a graphic example. Let's consider the equation sine of x equals a half from negative 3 pi over 2 to 7 pi over 2. It's shown here below in this graph. Notice that the x coordinates where the graph of sine of x intersects the line y equals 1/2, those are our solutions to our equation. So can you name the 5 solutions that are shown? This one would be 7 pi over 6 negative. This one would be positive pi over 6. And then 5 pi over 6. And this would be 13 pi over 6. And finally, this last one would be 17 pi over 6. There's a pattern there. And that's the question for part B. How do we represent all of those solutions of the equation? Well, the first one, theta sub 1, we'll call it. Let's consider from here forward. We started at pi over 6, and then we added or subtracted 2 pi k, where k is an integer. And that way, we could get both left and right by substituting k is 0, 1, 2, and so forth. So we get pi over 6 and 13 pi over 6. That would be this one and this one. Now the second set would be if we started at 5 pi over 6 and then added or subtracted 2 pi k, where k is an integer. And that would give us 5 pi over 6, 17 pi over 6, and so forth. So those are called general solutions to an equation. We did that graphically. In example 2, we want to solve graphically for using the unit circle. 2 cosine x minus 1 equals 0. So I'm thinking of this as the cosine of x. 2 cosine of x is 1. Divide by 2, where cosine of x is a half. Where? So we can solve that by saying x is the angle whose cosine is 1/2. Where does that happen? That happens at pi over 3. So we could also get the angle for a general solution by saying x sub 1 is pi over 3 plus 2 pi k, and x sub 2, if we went all the way around, this over here is 5 pi over 3, 5 pi over 3 plus 2 pi k. I'm calling this angle my theta sub 1 or x sub 1, and I'm calling this angle my theta sub 2 or x sub 2. For example 3, we want to solve each equation and give a general formula for our solutions. Sine of x is negative square root of 2 over 2. So we can think of the unit circle, and we're wanting x to be the angle where sine inverse is negative square root of 2 over 2. Well, that happens, remember on the unit circle, we're restricted on sine inverse. We can only think about sine inverse between negative pi over 2 and positive pi over 2. Those are our restricted areas. And I can think of the first one is going to be down here at negative pi over 4. So the first x would be, or the first angle measurement would be negative pi over 4. Now, that also happens over here at 5 pi over 4. So we could think of that if we did a general solution. We could say the first x would happen, x sub 1, would happen at 5 pi over 4 plus 2 pi k. And then the second one, I'm going to rename this, not thinking of the inverse, but I'm going to think of it as the positive rotation, being 7 pi over 4. So we could write it with positive angle measurements plus 2 pi k, where k is an integer. On example B, let's collect like terms. If 18 cosine, we subtracted 14 cosine, we would have 4 cosine on the left, minus 7 is negative 5. Then we could add 7 to both sides, and 7 minus 5 is 2, and then divide by 4. Cosine is a half. So cosine is a half where? Again, going back to the unit circle, I can use the unit circle as a visual here. Cosine is a half in quadrant 1. That happens at pi over 3. And it's also, cosine is positive a half in quadrant 4. So thinking of it that way, we can have x is pi over 3. And every 2 pi radians after that. And x is also, we could say x sub 1 and x sub 2 is also at 5 pi over 3 plus 2 pi k, where k is an integer. So two different ways to approach that. Example 4 is a technology question. We need our calculator, and we're solving tangent of x is 5. I'm thinking of that visually. If you look at the graph on the calculator with the asymptote at pi over 2 negative and pi over 2 positive, and the graph going through here, there's another one next to it. We want y equals 5. This is y equals 5. I'm looking for the intersection points. The first one, x sub 1. Remember, I'm using my intersect feature. X sub 1 is about 1.37, and then x sub 2 is about 4.51. So they're pi units apart, which tells us that we can write a general solution. Our angle measurement x would be, the first one, 1.37 plus pi k, where k is an integer. So they're going to repeat every pi radians. Same thing on B. If you look at the cosine curve, cosine starts at a maximum, maximum, intercept, minimum, intercept, maximum. We've got this oscillating behavior going on, and we want to know where the cosine is 0.6. This has to be 0.6. So y is 0.6 tenths. Where does that happen? This one is x sub 1, and this one is x sub 2, just like we had over here. This is x sub 1, this one is x sub 2. So the angle where that happens, that theta, I could call that theta, theta sub 1, which would be, this one's marked theta. Let's change our notation. So theta sub 1 and theta sub 2. For this one over here, our angle was x. This one, our angle is theta. So stay true to that notation. Theta sub 1 is about 0.927, and theta sub 2 is about 5.355. So we can rewrite that and say that we have theta sub 1 is 0. Let's round it to 2 decimals. The directions ask us to do that. 0.93 plus 2 pi k, where k is an integer, and then theta sub 2 is 5.36 plus 2 pi k. So these are our general solutions for that one. That puts us at the end of the first day. We've got a little bit of solving to do using the graphic methods and the calculator questions, and I'll see you for day 2, where we'll go a little more in depth.